It is a method for auto-normalizing a set of vectors in an inner product space. Next, the process takes a finite, linearly independent set, which is S equals to V1 up to Vk for where k is less than n. Next, it also generates an orthogonal set S prime equals to U1 up to Uk that spans the same k-dimensional subspace of real number as S. In mathematics, an orthogonal basis for an inner product space V is a basis for V whose vectors are mutually orthogonal. And for the step, this process consists of steps that describe how to obtain an orthonormal basis for any finite-dimensional inner product. Let V be any non-zero finite-dimensional inner product space and suppose that U1, U2 up to Un in any basis for V. We will form an orthogonal basis from this basis, say V1, V2 up to Vn.
So here is the step. Step 1, you let V1 equal to U1. Step 2, let V2 equal to this formula where W1 is the space spanned by the V1 and projection W1 U2 is the orthogonal projection of U2 on W1. The next step is you let V3 equal to this formula where W2 is the space spanned by V1 and V2. And step 4 is using this formula where W2 is the space spanned by V1 and V2.
Assalamualaikum warahmatullahi wabarakatuh. Okay, now I want to share with you about orthogonal basis. Okay, let's go. We start answer the question. Find orthogonal basis by a set of vector. Okay, we have x1 equal to 85 1 and x2 for 91 2. Okay, this is a set of vector. Okay, so we know that the loss is v1 equal x1. So we have x1 2 -5 1. Okay, we have two set of vector. We start to formula. That formula is we have v1, so we must find v2. v2 is equal x1 equal x2 minus x2 times v1 over v1 times v1 bracket time v1. That's okay. So we put the number of vector. x2 is 4 -1 2 minus x2 4 -1 2 times x1 2 -5 1 over 2 -5 1 is v1 times v2 times v1 2 -5 1 okay times v1 2 -5 1 so we get is 4 is x2 minus, after we calculate it we get 1 over 2 times 2 25 1 is v1. So we calculate it and get 4 -1 2 minus 1 -5 1 -5 over 2 1 next. So we calculate it, minus it, we get is 1 over 2. So now our answer is 3 over 2 3 over 2. That is we call W. Where is W is a symbol for complex orthogonal basis. This is process orthogonal basis. We call V1, V2. After we complex all, we call W as orthogonal basis complex. That's all from me. Thank you for.
Assalamualaikum and a very good morning to everyone. Today I would like to explain about Gram-Schmidt to find the orthogonal basis of R4. So this is the example of question, and let's try to solve it. So it is straightforward to check that the vectors v1 and v2 are linearly independent, and hence the set S is the basis of span S. Since the dot or inner product of v1 and v2 is equals to 1, hence it's not 0, so S is not an orthogonal basis. We apply the Gram-Schmidt process to generate an orthogonal basis from the basis S. The Gram-Schmidt process for two vectors is as follows. We define vectors u1, u2 by the following formula. Okay, so this is the formula, and then you just since we have u1 dot v2 equals to v1 dot v2 equals to 1, and u1 dot u1 equals to v1 dot v1 equals to 2. So now we compute, or we compute so now okay, so this is the compute. So we just put in this. We put in this into the formula. So V2 we put in here, and then 1/2 of V1. So this is V1, and then we solve it and we get this, and so now therefore the set is an orthogonal basis. Now it is an orthogonal basis. And also note that scaling by a non-zero scalar does not change the orthogonality of the set. So this is also an orthogonal basis of span S, just in case you prefer not to have a fraction. So that's all for orthogonal basis of Gram-Schmidt, and I hope that it helps, and thank you very much.
Okay, let's go to the example of orthogonal basis. For the question, V1 equal 1, negative 1, 1, V2 1, 0, 1, V3 1, 1, 2. For the first formula, U1 equal V1. So we put V1 here and get the answer. U1 equal 1, negative 1, 1. For the second formula, U2 equal V2 minus V2 multiply U1 over U1 multiply U1 multiply U1 here. So we solve this part first. V2 minus U1 multiply U1 over U1 multiply U1. V2 is here and U1 is here. So we solve the equation and put value of V2 also U1 also here and get the answer 1/3, 2/3, 1/3. For the last formula for orthogonal basis, U3 equal V3 minus V3 multiply U1 over U1 multiply U1 multiply U1 minus V3 multiply U2 over U2 multiply U2 multiply U2. So we solve this part first. V3 multiply U1 over U1 multiply U1. V3 is here 1, 1, 2, and U1 is here 1, negative 1, 1. So we solve this equation and get 2/3. So we move to solve this part. V3 multiply U2 over U2 multiply U2. V3 is here 1, 1, 1, 1, 2, and U2 is here 1/3, 2/3, and 1/3. We solve this equation and get the answer 5/3 over 2/3. So to get the answer U3, we put all the answer here and get the answer negative 1/2, 0, 1/2. These three vectors form an orthogonal basis.